Welcome to the Oscope Wizard. It is Baby Friday, and I am Gabe, the Oscope Wizard. You have made it to the Techno Lair on this wonderful Baby Friday. I was out walking this morning. It's in the 50s Fahrenheit because I'm in the United States and we still use weird imperial systems of measurement, which make very little sense. If we think about it, I do prefer the metric system, yet my compatriots here in the country do not and will not capitulate to this metric system, this nouveau way of measuring things based on tens and starting at the number 0 for temperature, which is a pretty good number to start at. No. We insist on starting at the number 32, which is kind of a weird number to start at, really, if you think about it. Actually, you don't even have to think about it. Just trust me. I was asking questions in the chat before the show started, and this one has got me stumped. Would you rather? It's a game I play. Would you rather? Would you rather? It's a card game. It's got a bunch of cards, and on it are printed scenarios that you have to choose between. The question from the card was, would you rather be better at math or better at history? And I wasn't even sure that history was a skill. History seems like the ability to remember things, and math seems more like a skill that one develops. So I wasn't sure how to be better at history, but I think if I had to choose, I would actually choose being better at history because it's more interesting than just being good at math. I mean, being good at math is useful, but honestly not that interesting. Being good at history, you would be able to have wonderful dialogues and really, give that real snotty reply where like, well, but actually, you would be the winner of all but actually arguments. In fact, if you were good at history, I think you would be auto win that game that nerds love to play. We do love the game, but actually, we can't help it. We can't help it. On the show today, what are we doing? We actually do have a plan. Let's get to the plan of attack for today. I have an agenda. Well, not really an agenda, a title. I have in my little software here, I call it the agenda, but it's really just the title. How does the Respeaker 2-mic Pi Hat even work? We have struggled on this journey to build our well, actually, in the chat there, well, actually, but actually, seriously, it's not an agenda, it's a title. We have struggled on this journey to build an IRL real-time subtitle necklace, closed captioning necklace. I'm thinking subtitles. That's what I turn on so I can hear things. We have struggled with getting this thing powered up. We've struggled with me ripping off ground pins, which was a bit unfortunate to the overall design. On the last episode, though, we were able to get our battery pack working. It's on the bottom of this stack of stuff. You can't even see it, but there's a Raspberry Pi right there, and there's my whole contraption to get at some GPIO pins. And there is the Respeaker 2-mic Pi Hat. It's a real catchy name. Real catchy name. I was curious how it worked. So, being the Oscope Wizard, I've actually hooked up my oscilloscope to check it out. This thing, if we are to go over, let's go over to the browser, sir. Can I make my browser work? I think that I can. Browser. There we go. We have a browser, I believe, on the window. We're looking at. You know what I wanted to talk about before we jumped into the Respeaker? My new SSH client. This is kind of a big deal when you're doing a Raspberry Pi. You have to figure out how you're going to talk to it through what series of terminals you're going to use. I had been using a Macintosh computer, which has a wonderful command line terminal just in the operating system. I switched over to a Windows computer through a series of unfortunate events. and have ended on a Windows computer because, despite the fact that it is bad at many things, it is very good at streaming video. So I have a Windows computer now to do this stream. What that means, though, is that I lost my terminal, my lovely Mac terminal. So to type in commands to my Raspberry Pi was less bueno on the Windows box. So I tried the terminal built into VS Code, which is a piece of software that you can use to write programs. I really like VS Code. The terminal wasn't awesome. I mean, in fairness, it's not trying to be an awesome terminal. It's trying to be a bare bones terminal. I went online to get Putty, which is it's a classic free terminal for Windows. It makes it really easy to communicate to things. Here's the website, putty.org. And on the website, they talk about this guy, Bitvice SSH client. Oh man, the chat is saying Sigwin, which you know what? I haven't even tried that one, but I did download this Bitvice SSH client right here. What I really like about it is that it has everything from Putty, plus it has an SFTP client built right in, and it automatically connects to the Raspberry Pi. And I didn't even have to type in a IP address. I was able to just type in the host name of the Raspberry Pi, which is unimaginatively called Raspberry Pi. And here is my, let's see if I can get this browser out of the way here. Please, get out of my way. Am I seeing it? Am I seeing it? I think I am. Here is my terminal. It's an SSH client, but in the background, I have the ability to drop files and grab files. And a lot of times when I'm working on my Raspberry Pi, I just need to grab a file off of it or put a file onto it, and this makes it super easy. I will have to give Sigwin, SCYGWIN. That is what Mr. Lewis is suggesting on the chat, and he is usually better at these things than I am. You live and you learn, though. I'm just trying to let you know tools that I found that actually work. This one is working out pretty well. But if we get to the point, the Raspberry or the Respeaker 2-mic Pi Hat, turn the browser on. You know what I should do? I just realized I should probably start my timer. I can already tell. I knew today was going to be kind of a long show because every time you pull the oscilloscope out and you start making physical connections, it just takes a little bit. I mean, you have to account for the time it takes to make connections. Oh man, okay. Another suggestion is that I could set up a Samba server, which lets me map my home directory to a drive on your computer. You know what? If you set up a Samba server, I'm trying to figure out how to just execute code in my VS Code that's installed on my computer and have it run on the Raspberry Pi automatically inside of the VS Code environment. And so far, I have not figured out how to do that. But Samba might be one way to experiment with making that happen. I also thought about putting VS Code on the Raspberry Pi, but that would require me to install a desktop, which I do not have on the Raspberry Pi Zero. I just have a command prompt. That's what I prefer on my Raspberry Pi, especially a Pi Zero, because this is a pro tip. The Raspberry Pi Zero is great at turning on and doing very minimal tasks. It is less great at running a desktop. But I could edit VS Code with Samba. That is true. But then I would have to launch it inside a terminal. So that's a good idea for just really quickly editing the code, though. I might experiment with making my Raspberry Pi a drive using Samba server. That's a pro tip. Thank you, chat. I appreciate it, Mr. Lewis. If I was to look at, so this is the Respeaker 2-mic Pi Hat. It has two microphones, one right here, one right here. I am probing over here, so there's a little trace. You can barely see it on the screen right there, but I'm actually probing the I think it's the resistor it comes out to. I'm probing the side of the resistor with a passive probe So I'm probing that microphone, and I'm also probing the I2S lines. So the way it is communicating to the Raspberry Pi, one of the ways that it is communicating to the Raspberry Pi is with I2S. And does it actually mention that? I don't know if it actually does mention it. Usually, I think people don't really care how it physically connects to the Raspberry Pi because they're just like, I slapped it on the GPIO header and we rolled. But you know, I wanted to know how it was actually connected, and it does use the I2S lines, which I have also probed. But if we were to go over to my favorite Raspberry Pi site for pinouts and select PCM for pulse code modulation for audio waveforms, you can see that these are my I2S lines. It's GPIO 18, 19, 20, and 21 spread out all over the connector and the header. That's what we're connected to. If I go back to my setup, we can see that really quickly. So I have my probe probing the microphone trace. And then on the side over here, I have my MSO channels from my oscilloscope connected to the I2S digital lines. So I'm going to look at, hopefully today, both the analog sound waveform and then the digital representation that is flying out of that GPIO line. This is my setup. It's not going to change. If I back up a little bit, we can see that I'm using my probe holder to hold everything in place. If we go around to the side here, I think we can get a better view of the digital lines so you can see how they're plugged into that header breakout board, which I think is really useful. And then all of that is fed back into the oscilloscope. So we have an oscilloscope back there in the background. It is my trusty RTO oscilloscope. I use the heck out of that oscilloscope. If I turn on my BNC viewer, I should be able to see my oscilloscope. So let's see if we can find these signals. Actually, that's my real accent. I do this fake accent for you guys while I'm doing the live stream. But I'm from deep South Georgia. Quick sip of tea. Oscope Wizard mug. Not selling them, just using this one because there's only the one. Hopefully you have a wonderful libation. Since this happens in the morning, we are going with tea. Maybe later in the day we could put a I don't know, a martini in the Oscope Wizard. This would make a very aggressive martini. This is a 14-ounce cup. A 14-ounce martini, I'd see you guys in a month. First step, since I have the physical connections made, the Raspberry Pi is on and active, I need to preset the oscilloscope, right? Get us back to blank slate because I was messing with it earlier and I'm not sure what its state is. So channel 1 is the analog waveform from my microphone. That's channel 1. I want to see where it is. I can see a little hint here. I got an up arrow letting me know that the signal is off the top of the screen. So I need to, well, one of the things I can do is I can adjust the vertical scale to just fit it on the screen and I can see, oh, there it is. There's my microphone signal. Sitting up at about 800 millivolts. So a microphone has a bias voltage that kind of pushes the whole signal up a little bit. I am uninterested in the bias voltage. That's generally a DC voltage. I am more interested in the up and down movement, the AC component of this signal. So one of the things I can do is I can go in and AC couple it. So that'll pull out the DC component and move that signal down to the middle of the screen. And now I can scale it a little bit more effectively. So if we zoom in here, you can see it's bouncing up and down, which is a real good sign because it's a microphone, right? So as I talk, as I get closer, in fact, it should get bigger and bigger and bigger and ah! All right, our microphone's working. You can see that's the actual analog signal. I'm zoomed way in. Human speech doesn't go at a resolution that is this tight. It would be 100 nanoseconds of sound would be, you'd be hard pressed to get any good information out of that. But if we were to zoom out and get a little bit more sound, or not a little bit more, well, a little bit more sound by getting a little bit more time. So I'm gonna zoom out here. Maybe we'll get 500 microseconds. So now I'm zoomed out, but you can see I got a lot of noise on the signal. So one of the tricks that I do when I'm working with an audio signal is I limit the bandwidth. So right now the scope's saying, hey, I'll allow 500 megahertz of bandwidth into the front of the scope. Audio, on the other hand, does not do 500 megahertz. In fact, we could go over and see what we should do. There's a really easy way to do this. First of all, your ears have a limited bandwidth, but maybe you're not going to go by your ear holes. Maybe we want to go by the actual thing that we're measuring, which is generally a good thing to do. So the pi hat, let's see, this pi hat uses the WM8960. So we should be able to look up WM8960 and see if we can find a data sheet to tell us anything about it. You know, I do love those data sheets. Can't get away from data sheets. It feels like there's a lot of data in data sheets. Is that? That's true. I'm doing a dad joke for that, but there's a lot of data in data sheets. W8960 product data sheet. Let's check this out. Okay. It looks like 48 kilohertz is about what our bandwidth, or that is the sample rate. It is a 24-bit ADC and DAC. 24 bits is a lot of bits, and it can go up to 48 kilohertz on both the DAC, that is the digital to analog converter, so that is the microphone side, and it also has a speaker output, which is the ADC to go from analog. So I got that backwards. The DAC is the speaker output, 48 kilohertz, and the ADC is the analog to digital converter. So this is the thing that is converting my voice into those I2S packets, presumably, if we ever get there. But you can see it operates at a pretty low frequency, 48 kilohertz. And I just said our oscilloscope was measuring this thing at 500 megahertz, which is a good bit more than 48 kilohertz. So let's slow this down. Let's slow it down to like a megahertz. And my sample rate does not need to be 5 gigasamples. It could be 50 kilosamples, I think. What's the min we can do here? Min, megasamples. Let's just go down. Down, 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 down. Record length. I have a button over here. There we go. Let's move out and we can go down lower. You can see your voice is actually fairly slow compared to what the oscilloscope's capabilities are. But there we are. There's my voice. You can see it on the screen. It looks like, when you do those weird voice, what am I thinking? The weird voice visualizers on your old MP3 player. I'm thinking Winamp. Winamp. If you can remember, Winamp used to have all these weird visualizers. And some of those, some aftermarket radios still do this. But this is what all of those visualizers are trying to mimic. An oscilloscope looking at a microphone output. Now, let's turn on my digital lines. If I can figure out how to do it. Here we go. Oh, right here, right here, right here, right here. Am I doing this right? I don't know why I'm asking you guys. I can't ever remember how to do this through the interface, but I want to. There we go, serial bus. Let me just hit the button. I got a button right over here, logic. There we go. That's what I wanted to do. Let's turn on these 4 logic lines. So I have my signals connected to D0, D1, D2, and D3. That is I go back to my browser real quick. Clock, frame select from I2S, data in and data out. One of these D3 and D2 are, one's data in and one is data out. Of course, I can't remember, but there's a really easy way to figure that out. It's like, one is when the data goes from this Pi hat to the Raspberry Pi, and one is going to be when the data comes from the Raspberry Pi back out to the Pi hat. So right now you see I'm talking, the microphone's picking up the sound, but no data is going on these digital lines. So the Pi hat is not sending the Respeaker to my Pi hat. The Respeaker, let's just call it the Respeaker. The Respeaker is not sending data to the Raspberry Pi, not audio data. So I need to ask the Respeaker to send audio data. And this was kind of blowing my mind a little bit, because when I designed my amplifier before, these lines stayed active all the time. And that is probably a poor design on my part, which gives me some ideas the next time I do something with audio, is I need to control these data lines a little bit more, because the more information I'm sending, the more chance noise is going to happen. And if no noise is happening, I could turn those data lines off and actually save power. Let's go send a command to the Raspberry Pi. I think if I'm going to make my VNC viewer a little bit smaller here. There we go. VNC viewer is smaller so you can see the oscilloscope while I am typing commands to the Raspberry Pi. I want the Raspberry Pi to record a something. Record me talking. So if I do a record, I think I do a record. Let's do a record -F DAT. That'll just tell it to do this thing at the bottom, which is a 16-bit file at 4800 kilohertz stereo. And let's save it to temp.wave. So we're just going to make a recording and save it to a file called temp.wave. Does it work? We are talking. You'll notice that as I talk, you can see the waveforms happening on the microphone, but you can also see the digital lines happening all of a sudden. So now if I stop it, so I'm going to stop my recording, boom, digital lines go quiet. They're gone. There you go. So that means that the Pi hat, the Respeaker, only sends data while I'm actually recording, or if I'm playing it back. So if let's play this back. So I have a speaker right here. I turn back on there we go. I have a speaker right here. We'll turn it on. I have it hooked up with the cable. Oh, old school. Not Bluetooth, but with a cable. I'm going to set it right there so you can see it. And let's see if we can make sound come out of it. I think we can. Let me just, let's just send a command to the Raspberry Pi. I can turn back on my terminal here. There we go. Let's send a command, and we'll turn back on my oscilloscope so we can see the oscilloscope signal in my command. I think it's just a play temp.wave. So I'm just telling the Raspberry Pi to play this file called temp.wave. You're talking. Notice that as I talk, see the waveforms happening on the microphone, but also see the digital lines happening all of a sudden. So now if I stop it, so I'm going to stop my recording. Oh, I didn't hit it fast enough. Let me try that again. I was trying to grab the the waveform. Let's just do this. We are talking. There we go. Notice that as I talk. I think I can stop me from talking. There we go. Okay, we've made a capture here. I stopped it so that we can actually look at it for a second. Let's make this big. So this is our waveform on the oscilloscope. I have the microphone, which is channel 1. If I drag this up here, got the microphone. So that is my analog waveform. And down here are my digital waveforms. D0 is clock. D1 is frame select. And D3 must be data in, data input, because it is the data from the Raspberry Pi to the Pi Hat. And the Pi Hat is going to use that WM8960 chip, that audio codec, to convert this digital traffic into this waveform. So if I zoom in, actually, I should be able to see the ones and zeros down here. So look, boom, ones and zeros. That is a good sign. I think I can even, yeah, zoom in a little bit more. It looks like I may be undersampling this data. So what do I mean by undersampling the data? These don't look like ones and zeros, do they? They don't look like nice square waveforms. They look kind of like weird blips that indicate I have not got enough sample. I've not looked at this waveform fast enough to tell you where the ones and zeros should be. I can see there should be transitions about right here, but I'm not giving you the full picture of whether it's a 1 or a 0. So I could increase my sample rate to grab a better picture. I'm not sure how fast I need to increase the sample rate to make this all work, but I suspect, if I remember right, I actually have to have the sample rate pretty high on these digital channels to make it all grab it. Let's crank it up to 1 megasample and hit run again. Let's see what, actually I can just hit run. I could record myself again. I'm going to record myself again, and now you can see, boom, here we go, here we go. Now we got what looks like ones and zeros. Am I right? Am I right? Yes, that looks like ones and zeros down at the bottom. So before, we had signals on this bottom digital trace, D3, which was data in. Now I'm using this to record, so data out is active, because I'm sending data from the Respeaker to the Raspberry Pi. This is the digital link. This is the that Respeaker codec is converting this analog waveform to these digital waveforms. Anyway, that's how it works, guys. That's how it works. That's the oscilloscope at work. This is a great place where an oscilloscope works. But let's get back to the project. The project was not making measurements on the Respeaker, although that was part of the project. You have to measure what you're building to make sure it's all working properly, especially if you run into trouble. Having a measurement there and being able to see what the signals look like can help a lot. Oh my gosh. Oh my gosh. Hold on. Hold on.
5 minutes remaining.
So let's get back. 5 minutes. I'm going to set the timer again. You got to set these. I got to use these timers. If I don't use these timers, I get out of control. Quick sip of tea. Hopefully people are still following along. This is when you get down to the nitty-gritty meat of the matter, sometimes it can get a little bit boring, unfortunately. Again, math over history. I still think math over history. Or no, it's history over math? History over math. What am I saying? I'm saying it backwards. Okay, so we talked about the codec. Now let's get back to the actual project. The project is trying to do offline speech recognition. And I came across this article, which I mentioned in a previous episode, from Seed Studio, and it first appeared in Hackster.io, which is got all kinds of cool projects. But it is using the Raspberry Pi 4 with this Respeaker module that I have, the Respeaker 2, to perform offline speech recognition, which is a big part of our goal. When we have this necklace on, we might not be on the internet, and so we would like the Raspberry Pi to do the speech recognition and the speech to text offline without an internet connection. So this guy found that Mozilla's Deep Speech ASR, which I noticed this is a pretty common acronym when I was doing some Googling, automatic speech recognition. It works well on the Raspberry Pi, and in fact, so well so well in here it claims to be faster than real time, which we decided in the last episode was beyond the scope of our project because we aren't going to jump into time travel. When I tried to load deep speech on my Raspberry Pi, in fact, here we are, Raspberry Pi 4/3B. Let's do it. Pit 3, install. Let's copy it. Let's go over to my browser or my what do we call this thing? Terminal. Let's pop it in there. See if we can install it. I was really excited because I thought this was going to be my hookup. I thought, honestly, that I was just going to follow the instructions that he kind of lays out in his article and end up with a thing that could recognize speech and display the text. That's what I really need to get. I need the system to recognize speech, display the text, or output the text in a manner that I can then manipulate because I want to get the text onto some LEDs. Because otherwise, nobody can look at a tiny... Also, you're not carrying around a computer screen with you. You're carrying around LEDs. That's what we have. This is what I ran into. Could not find a version that satisfies the requirement for deep speech. No matching distribution found for deep speech. So then I looked and I thought, certainly, it doesn't really require a Raspberry Pi 4, does it? That I kind of blew right through that part, but this turns out to be a hard requirement. A Raspberry Pi 4/3B. I have a Raspberry Pi 3B, but that's not what I want to put my project on. I might ultimately have to upgrade because of processing power, but I wanted to try to make it work on the Raspberry Pi Zero. Zero! That's the trick. So I started doing a little bit more Googling, and I came across this thing called Pocket Sphinx on a Raspberry Pi. Pocket Sphinx is a super lightweight speech and voice recognition engine. It's used in a project called Jasper, but it's offline. So it's got its own voice database inside, and you can install it on a Raspberry Pi Zero. It does take a little bit of time, but this page right here walks you through the process of downloading both the speech database and the Pocket Sphinx engine. I do have this working to the extent that it can actually use a waveform file and decode the waveform file into actual words. So I think on the next episode, we'll probably dive deeper into Pocket Sphinx, which is going to be my first attempt at getting automatic speech recognition working on the Raspberry Pi. But I'm going to be open to suggestions if anybody else has a better automatic speech recognition engine that works offline. Of course, I mean, there's Google and Alexa both staring you in the face. They're available to try. I want to do it offline. That's what I really want to get at. I want to see how powerful and how fast the Raspberry Pi Zero can be when it comes to automatic speech recognition. So I've probably placed too many caveats on my goals and too many, I might have boxed myself in, but having a box in a design is actually, I think, good in many ways, because if you don't have a box, your design just keeps going on and on and on, and kind of bounding it a little bit gives you an endpoint to shoot for. So our endpoint is offline speech recognition on a Raspberry Pi Zero. That's what my endpoint now is. If I have to adjust my box and make it bigger and change my box, I can do that. But I want to explore all the possibilities in my current box. So, thanks for watching. I appreciate it. It's a great Baby Friday. Hopefully, you guys enjoyed nerding out with me in the techno layer and are enjoying the project. We got a lot of measurements done today. We saw how the Respeaker 2 works when it comes to getting that microphone data into the Raspberry Pi and then the audio data from the Raspberry Pi back out to either speakers or headphones. So, I mean, I think it's cool. I love sound though, and I love messing. I love messing with little, hobby projects. I don't know all the nerds in the world, but I'd love to meet them. So please share this with a nerd in your life, and I'm going to hang out in the chat. I'll see you guys next week. Take it easy. Bye.